Welcome back, my young thinkologists. Today's quick chemistry fact is about the atomic model of the atom, specifically the modern atomic model of the atom. Modern atomic model. And the individual who played a major role in the modern atomic model of the atom is Niels Bohr. Very famous quantum physicist. He basically said this. He looked at Rutherford's atomic model, which, as we all know, kind of looked like this right here, which was a solar system-like model, and he said, okay, if this is going to work, atoms have to have defined orbital shells. The electrons have to be in these defined orbital shells in order for this to work. He also said that these orbital shells themselves actually have defined shapes. And the math involved to find this, everybody, if you've ever heard of quantum mechanics, yeah, it's very tough math that's involved in actually determination of a lot of this stuff. Now, more importantly, these shells and these shapes are quantized. Quantized. Now, all that means is to be quantized is to limit something to a set number of possible values. So the set number of values is actually the shells. You'll find out that you could go to an infinite amount of shells on an atom, and that electron in that outermost shell won't even play a part in actually being on the nucleus or near the nucleus of that atom. So we actually have to quantize the actual physical amount of shells for this to work for even the largest atoms on the periodic table. And let's show this. If we look at helium, let's look at helium. That's a good one to start with. Helium has 2 protons. Helium also has 2 electrons. And lastly, helium has, let me pick a nice color here. Well, let's pick yellow. Helium has 2 neutrons. Okay, that's a fact. You can get all this information out of the periodic table just by looking at the atomic number of helium and the mass number of helium. So I'm just going to kind of draw in little circles here. So there's 1 proton. Here's another proton, and let's put some electrons in here. Sorry, not an electron. Yeah, oops, let's go ahead and rechange that color. Let's put yellow for neutrons, right? Okay, so a neutron and a neutron, right? So 2 neutrons and 2 protons. Now, according to Bohr, the electrons are in set positions. They're in set shells. The question is, how many can I have in each of these shells here? The n equals 1 shell right here, and the n equals 2, and n equals 3, and actually n equals 4, n equals 5, n equals 6, etc., etc. And actually, a thing to note, the further out you go, the closer that these shells get. That just has to do with keeping the outermost electrons intact with the nucleus of the atom and holding stability across the board here. But relating back to determining exactly how many electrons we have in our shells. Now, n equals 1 has only 2 electrons that it's able to hold. That's just because it's so darn close to the nucleus. The nucleus will actually hold those suckers in real tight. They're not going anywhere, okay? And actually these electrons are, in fact, moving in defined orbital shapes around the nucleus of this atom, okay? Let's go to another example. Let's look at, oh, I don't know. Let's just look at the next one. Let's look at lithium. Lithium, okay, that's on the number 3 on the periodic table of elements, atomic number 3. And it has, everybody, 3 protons. If its atomic number is 3, it has 3 protons. It also has 3 electrons. And if you do some math and subtract 7 from 3, you actually find out that it has 4 protons. And I'll use yellow. Sorry, not protons, 4 neutrons. Okay, because its atomic mass is 7, so 4 plus 3 is 7. Okay, let me draw some protons. So 1, 2, 3. There's my protons. Let me put some neutrons in. So 1, 2, 3, and 4. Now if you're wondering, okay, how did I decide where to put these? I'm just putting them in random order here just to represent the nucleus, okay? So this is 4 neutrons and 3 protons in lithium. Okay, everybody, where do you think these electrons are going to go on n equals 1? Well, like I said, you can only hold 2 electrons in the lowest energy level, which is n equals 1, so automatically you're going to have just 2 electrons. And then where do you suppose this next electron is going to go? That third one is going to go on n equals 2, n equals 3, n equals 4, n equals 5, etc., etc. Well, it'll just start to fill the next orbital level. So we're just going to have an electron go into the next orbital level. And notice we only have 1 electron in the n equals 2 energy level. Guess what? Those electrons actually have a name. We call those, in chemistry, valence electrons. They have their own name because they are important. Hey, do you all remember how we get an ion? What happens to lithium if this electron goes out? Well, we're left with more positive charge right here. So we actually get, notice, no longer lithium, but you get lithium plus. And that's just due to this valence electron here jumping off the orbital shell. Okay, so notice the information does go full circle. Let's do another example. Let's look at, I don't know. Let's look at a noble gas. Noble gas. And I'll talk about why we call it a noble gas. It wasn't developed by a king or any royalty. Let's look at neon. Neon, if you look at the periodic table, has 10 protons. It also has 10 electrons. Oh, wrong color, sorry. 10 electrons. And 10 neutrons. Yes. I'm not going to draw these all in. Let's just go 10 neutrons and 10 protons, okay? So 10 neutrons, 10 protons in the nucleus of neon. And let's fill in our electrons, everybody. So 1 electron and n equals 1, 2 electrons. Where are these extra electrons going to go? We only have 8 left here, right? 10 minus 2 equals 8 electrons left. Well, turns out every energy level after n equals 1, you can fill with 8 electrons. And that is actually very significant. It actually plays its part in naming neon as a noble gas. 8 electrons, it turns out, is very, very suited by every single element on the periodic table. 8 electrons in the outermost shell is very suited for just about every element on the periodic table. And that's just because 8 electrons, everybody, fills its octet. An octet is when all valence electrons, all 8, I'm going to substitute VAL for valence electrons, fill the outermost shells on an atom and causes it to be what we call in chemistry an inert gas. In this case, neon's a gas, so it is inert, meaning it cannot react with anything readily. And actually, in fume hoods of most sophisticated chemical processes, they actually use not neon, but they actually just use argon gas because it's so darn inert. It's so noble. The electrons really resist change to anything present in that fume hood. Okay, so the thing to take note here is The electrons are in defined orbitals, so notice at n equals 1 we have 2 electrons and only 2 electrons. At n equals 2 we actually have 8 electrons, and the number goes up. The more electrons you have, you just keep filling them up until you can't fill any more, okay? So that is it. I look forward to seeing all of you tomorrow in class. Enjoy the rest of your evening, my young thinkologists. Have a great day.